Hey, good morning, everyone. Welcome and thank you for joining us for the 5th installment of our virtual tech tour series. This morning, we're going to be getting into all things dosing or metering pumps. I'm Dustin Wheatoff, Vice President in Sales at Crane, and very happy you could spend a little time with us this morning. Before we get into the training, we did have just a few housekeeping items we wanted to cover. We have a couple videos we're going to be playing throughout the training this morning, and the audio does tend to work better if you're logged in from a computer. So if you have the ability to do so and you're not already, please join us from a laptop or PC. If you have questions as we're moving throughout the training, there is a questions box that should be available to you. Please enter any questions into the questions box. We'll be sure to address those at the end of the training. And we would really appreciate your participation in a short survey at the conclusion of the training. It's important for a couple reasons. Number one, we want to hear from you guys how we're doing, anything we can do to improve, topics you'd like to hear about in the future. And also it is necessary for us to confirm your participation and facilitate getting you your DNR or CE credits for those of you that signed up for those. We have a couple interactive poll questions throughout the training. We'll practice one of those here in just a minute, and we would certainly appreciate your participation in those as well. And then a reminder that a recording of the presentation will be made available for future reference or to share with others in your organization who maybe weren't able to attend this morning. For your presenters this morning, I'm pleased to introduce Tom Schroeder from Crane Engineering and Brad Slagle from Grundfos. Tom is a mechanical engineer, started with Crane about 10 years ago as an application engineer, and is now currently managing our distribution business unit. So he's responsible for a majority of our inside sales and application engineering staff. And Brad Slagle also started as an application engineer with Grundfos about 7 years ago. Today is a senior account manager and is a subject matter expert on water treatment and dosing technology. So very, very happy to have Tom and Brad presenting this morning. And now we'll get into our first polling question of the day. So we are curious, an easy one to start off. What brings you to the tech tour this morning? Are you currently experiencing some issues with dosing pumps or dosing applications? Are you looking to just brush up on your general knowledge of dosing technology? Or are you just here for the DNR or CE credits? So we'll give you a second to answer that. All right, looks like a few of you are currently experiencing some issues, a few more here just for the credits, and then a majority just looking to increase your general overall knowledge of dosing pumps. So fantastic, appreciate you guys participating in that. And without further ado, I'll turn it over to Tom and Brad.
All right, thank you for coming today to our Dosing Pump Basics tech tour. Excited to be talking about dosing pumps today. It's one of, I guess, my favorite products when I'm selecting, just because it is a good change of pace from selecting centrifugal pumps, other PD pumps. Just like some of the features, there's variance between manufacturers, and just like selecting these pumps, to be accurate for different applications. So just going to go through our learning objectives for this morning. By the end of the tech tour, you should be able to describe where and why dosing pumps are used, explain the mechanics and common dosing pump designs, demonstrate basic steps to selecting a dosing pump, describe different control methods that are in different technologies, and identify good installation and piping practices. So here we will kick off another polling question. Question is, what issues have you had with dosing pumps in the past? Pumps not dosing accurately, issues with air entrainment or priming, problems with materials holding up to the chemicals pumped. Okay, so it looks like the kind of consistent across the board, mostly with issues with air entrainment and priming. Problems with the materials holding up to chemicals being pumped. So we'll talk about a few things today that might help you out in those areas. To kick it off, I will turn it over to Brad from Grundfos.
Very cool. Good morning, guys. Thank you, Tom and Dustin, for having me. So what I'm going to start out here is kind of a higher level overview of dosing, some of the terminology, some of the products, what you see in the field now, and kind of roll from there. So first thing you'll see here, there's a variety of names for dosing pumps, right? Here at Grundfos, we call them dosing pumps, dealing with engineers through specifications, customers, you know, even at the plant level, there's a multitude of different names. You'll see them all here. These are kind of the most common. Chemical feed, chemical metering, or dosing pumps are probably the three most common. But yeah, they all mean the same thing. So per Hydraulic Institute, as we'll see on the next slide, a chemical metering pump or a dosing pump, whatever you want to call it, is a reciprocating pump designed to accurately displace a specific amount of volume over a specific amount of time. So a little different than centrifugal pumps that you may be used to. Centrifugal being an impeller with a shaft, spins in a either clockwise or counterclockwise rotation to give an approximate flow and pressure at much larger volumes, right? So they're pumping into gallons per minute, whereas the dosing pumps are designed for gallons per hour. So you're dosing a neat amount of chemical into a heavier process, and as I'll touch here in a little bit, the accuracy is key with these, right? So that's why these were designed in this fashion and not as a centrifugal pump. Here's kind of a multitude of different styles and configurations. So here you see on the left, this blue one is a traditional solenoid pump. So this is a little bit older style. These are typically controlled with a stroke frequency, meaning how often the diaphragm moves, and then a stroke length. So between how often the diaphragm moves and how far the diaphragm moves, you're able to achieve a certain flow rate or set point. These are noisier, tend to be noisier. It sounds, every time the solenoid fires, it hammers, so you sound like a loud clicking noise. That's an easy way to identify a solenoid. Then you have a mechanical diaphragm. So this is a standard motor-driven dosing pump, typically seen a lot in classified explosion-proof applications. So power plants, this is common. Anything that requires an explosion-proof environment, you see a lot of these mechanical diaphragm. The hydraulic diaphragm you see on the right, this is typically a higher pressure pump. So a little bit different than the mechanical. They look very similar. It's driven by a standard asynchronous NEMA frame motor, but there's no connection between I guess what you would call the diaphragm and the pump end shaft. So it's a cavity filled area with oil, and the oil compresses and triggers the diaphragm to move, and that's what creates the higher pressures. Mechanical and the hydraulic are both older technologies, but that you still see them in high pressure applications and explosion proof applications. This one on the bottom right, this motor driven multiplex, I think is a very uncommon. I've seen it once in my years of working in this industry, and it was at a surfactant plant in Chicago. But this is it's one motor driving multiple pumps, anywhere I think from 2 to 6 or 7 metering pumps. These are typically for classified explosion-proof environments as well. And then what kind of Grundfos prides themselves on is this one here in the middle, this red one. It's a stepper motor driven. It's an electronically driven motor, a little bit different in terms of technology. So we control the stroke speed. So instead of controlling the frequency and the length, we control how fast the diaphragm actually moves, and it gives a little bit different approach to the chemical metering pump business. Benefits, as I spoke a little bit earlier, dosing pumps are designed for high accuracy, right? So in a given water treatment application, the biggest cost consideration is actually the chemical. And it's not typically any of the equipment or components of the dosing system, but the chemical itself. So it's very important that the user, the engineer, is able to achieve a high level of accuracy. Process control, so a lot of the dosing pumps these days allow for automated control. So this gives remote control and monitoring. It requires less manual intervention and just kind of a more sustainable and smoother process. These chemicals or these pumps are designed to obviously handle hazardous and expensive chemicals, right? So in pH, you have sulfuric acid and a caustic, sodium hypo and disinfecting. So as the more the neat chemical gets, the more important that your dosing pump is selected correctly. Deaeration, so it's important. I think one of the poll questions earlier, one of the biggest issues was air entrapment with off-gassing chemicals, like sodium hypochlorite being a very off-gassing, high concentration of air chemical. It's important that a dosing pump is correctly designed to handle that off-gassing. And then there's the last two, auto flow adapt and positive feedback, kind of relate to the second bullet point, and they give remote control and monitoring of the system, and kind of develop some brains for the entire process. So why is it important, right? So as I alluded to in my last slide, you have a lot of hazardous and corrosive environments and chemicals, and it's important that accurate dosing helps mitigate some of the extra expenses, right? Both manpower to deal with, and I think this was on the polling question as well, materials compatibility concerns, spills, and the extra legwork that comes from those sorts of problems. And then also accuracy, then the higher the accurate the dosing pump is, the less often you're having to replace the chemical, which is a cost savings, right? So if you're dumping too much chemical, as I think I get to in my next slide here. Yeah, so as I noted, the chemical cost of this is typically the most important. If you underfeed an area, you're under treating it, so your water is not treated as properly as it should, right? And that's obviously not good for your system. That creates quality concerns for the product, and it's not a good situation. Then on the other side, if you overfeed, so you have the same sort of problems as underfeeding, as you likely have an inferior product. You can run into quality concerns with the water, but then that's also a tremendous cost. So if you're refilling your chemical tote too often, that's an unnecessary cost. So where you want to be is in this blue area, right? Anywhere in here, kind of at the top of the bell curve, ensures the most accurate and the kind of the target range you want for the chemical metering pumps, to ensure you're getting both a high product at the end, high quality product at the end, but then you're also mitigating some of those chemical costs. So how is the flow rate determined? This is kind of a multitude of factors, including the amount of flow. You typically have a parts per million that's required, or a concentration of chemical that's needed to mitigate, either move the pH up or down, or a certain parts per million that's needed to clean the water. So you typically need to know the flow rate and the process line. So I'll show here in a little bit later, there's a typical setup for the pump in which the chemical metering pump is always dosing into a larger process line. You need to know the flow rate of that process. You also need to know the pressure of that line. So you have to be sure that the dosing pump is able to overcome the pressure in the process line. Otherwise, you'll just be siphoning water from the process line back into the dosing pump, and that's not a good situation either. In order to determine flow rate, as the last two bullet points here, you need to understand the concentration of your chemical. Typically, the more accurate pump you have, the more neat chemical you can provide. A more neat chemical dumped at a much lower flow rate, but maintaining accuracy is typically a cost advantageous application. So if you can dose a higher chemical, higher concentration chemical at lower flow rates, you're typically using less chemical, and that's a considerable cost savings measure. So kind of the three big factors are knowing your flow rate and your pressures, your concentration, your chemicals, and that kind of helps you determine where you need to be in terms of sizing a dosing pump. One of the biggest issues we're seeing here as it becomes more, I guess, controlled at a state and federal legislature level is Legionnaires. So Legionella is a bacteria that grows inside of system pipings, typically in hotels, we call multi-occupancy buildings. So hotels, apartment complexes, hospitals, office buildings, and high rises. It's a bacteria and a biofilm that grows on the inside of the piping. Once it breaks off of the piping, it becomes a bacteria that is ingested, not through drinking, but typically through aerosols, through like mist. So if you stand outside of a water fountain or a water feature and you kind of feel the mist, there's often, if not treated properly, there's could be Legionella bacteria in that mist. Typical ways to treat Legionella, you see a lot of copper silver treatments, hyperchlorinate. So you can dump high levels of chlorine into the process, but that often, if you ever showered in a hotel and you've taken a shower and you kind of taste the bleach, that's exactly what that is. So they're hyperchlorinating their systems to treat Legionella. UV is also common. So there's a UV filter or UV light somewhere in the process designed to kill the bacteria. You can treat the water up to, or heat the water up to above 140 degrees Fahrenheit, but that's often not, I mean, if you in a hospital, can't turn a shower on to 140 degrees, right? That burn you. So that's typically not used very often. What we're seeing more and more as legislation changes, states are starting to adapt and require certain levels of testing and treatment is chlorine dioxide. So chlorine dioxide is the only proven, I believe, chemical to kill the biofilm once it's inside the pipes. And if you've ever met anyone with Legionnaires or know anyone, it can be a fatal disease, but typically it's a disease that's chronic, right? So once you're diagnosed with Legionnaires, it's not something that's easily treated or goes away. So typical applications, right? Most of this we would call industrial. So your common food and beverage, pulp and paper, power plants, those sorts of applications all use some sort of chemical metering, some sort of water treatment. But for the most part, all those chemicals used are the same, right? So you'll have like a sodium hypo, typically 12.5% that's used for disinfecting or cleaning. You'll have sulfuric acid, typically 93% used for pH balance as an acid, and then a caustic, I believe it's 48%. Sodium hydroxide as pH control as well. So all of these applications, all of these end users and markets will use chemical metering pumps, water treatment. They've all got an influent water, a process they need to treat, and then when it becomes effluent, they either reuse it or they send it back to the city. And along the way, there's multitudes of different water treatment applications. Yeah, so that touches on here a little bit more. So this gets into a little bit more wastewater. Wastewater treatment is sometimes uses different chemicals than industrial water treatment. So municipal wastewater, industrial wastewater use a lot of flocculants, right? So alums, ferric chlorides are very common. are very common chemicals to use in the wastewater industry. What it's trying to do is those sort of chemicals attach themselves to particles in the water, create a heavier solid, and then they fall to the bottom. So basically what you're trying to do is filter out the larger particle size bacterias. You see a lot of calcium hypochlorite in commercial applications. So public water supply, swimming pools, cleaning systems, anything like that, that acts as just a lighter version of a water purification. So all that's doing is cleaning and scrubbing the water. Yeah, so why do we need to treat water, right? The biggest issue, and all of these touch on different portions of the water treatment process, but you need to make sure that you have a properly treated water for whatever your application is, right? Typically that's for quality control. So if you're using the water as a reuse product, or if you're using the water as part of your application, the more properly the water is treated, the higher quality you have, higher water quality you have. At the end of the day, you're going to have a higher quality end product, right? The other side of this is there's legislation and there's governance around dumping water back into the city, and the city requires the water before it's sent back into the city to be at a certain property, at a certain level, in order for there not to be additional fees. So you have to make sure, and I'll walk through. Yeah, here's kind of a process, water treatment process at the wastewater level. So you kind of start here at the beginning, right? Here's your influent. This is coming from the city. This is coming from the buildings. The water comes in, and it's typically we call physical treatment. So it goes through screens. It goes through some sort of grease and grit removal, and what it's doing at that point is removing the heavy solids. Then, as I touched on a minute ago, it goes through typically a flocculation treatment, where chemicals like alum are added to the process. They attach themselves to the remaining solids and they fall to the bottom. That water is then, the solid water is treated as sludge, and then the remaining water moves on to the primary treatment. So that's when you add the sodium hypo, you add the pH, you adjust the pH as it's needed. You send the water through deaeration tanks, you scrub the water. There's all sorts of different processes that are used along the water treatment processes that are used along the way to make sure the water remains at a certain quality. Then at the end of the day, there's kind of two different options, right? So once you've gone all the way through the treatment, you're done with the water, you can either dump it back into the city, so you can send it back into the municipal water system, or what we're seeing a lot more now is water reuse systems, right? Companies are trying to become more sustainable and less reliant on external resources. So everyone's doing their best to reuse some of the water that they've treated. So reused water would go through the process and be recycled to go back through the process again. This water reuse buzzword is a newer technology. It's a newer movement, but it's something that is catching on here pretty quick. You're seeing a lot of resources utilized trying to implement water reuse systems. And here's some of the, I've focused on and mentioned some of these a little bit. These are kind of we call this our 80-20 rule, right? So 80% or roughly of the water treatment industry uses some variation of these. Sodium hydroxide being a caustic, this is used in pH adjustment, very common in municipal and industrial. Same thing with sulfuric acid, you see there at the bottom. So that's the acid portion of the pH control, also used in industrial, heavy and industrial, and municipal. Sodium hypochlorite then is commonly the third among the three. It's the cleaning, so it's the disinfecting bleach, and it's what disinfects the water. Ammonium chloride, also known as alum, this is a flocculant. So this is, as I stated, this is added to the water. It attaches itself to the particles within the water, becomes a heavier solid and falls to the bottom. Ferrous sulfate is heavily used in municipal. It's an odor control substance. So you see this a lot used in local municipalities. Everyone's probably got a local water treatment pump house in their neighborhood or in their city. And ferrous sulfate would be commonly used to as an odor control. Calcium hypochlorite, I mentioned this a little bit earlier. This is commonly used in commercial applications, swimming pools, any sort of potable water where you need to clean and drink, interact with. You see a lot of calcium hypochlorite.
Okay, thank you, Brad. And so we have our next polling question here. What pump technology does not reduce stroke length? Is that a hydraulic diaphragm type, solenoid driven, mechanical diaphragm, or a stepper motor? So it looks like we've got an array of answers here. The correct answer is stepper motor, which most of you got correct. So let's work. Okay, so now we're going to jump into dosing pump features and designs a little bit here. First, we're going to talk about the very basic components that each dosing pump is going to have. Right now, we're taking a look at a mechanical type diaphragm pump, but the features in some form are going to be in any of these different designs. You're going to have a motor. This is showing a NEMA, just a typical NEMA motor that is seat-faced to the drive assembly. Your drive assembly is what's going to turn that rotary motion into linear motion to get that reciprocating motion. And then you're going to have the liquid end where your chemical is being processed. We'll get into liquid end design in a little bit. And then typically you're going to have some different control features. This one in the upper left-hand corner, we are just showing a manual control knob that would adjust the stroke length. So what type of drivers are available? We just looked at a pump with a conventional, NEMA frame motor. You've got the solenoid type and the stepper motor. So we're going to take a look at each one of those and how they operate. Brad broke down already into two different basic types of actuated diaphragm pumps. So you got hydraulically actuated and mechanically actuated. The difference there is how the piston is pushing that diaphragm in and out. First, we'll take a look at a hydraulic diaphragm liquid end. So just talking about the liquid end, a lot of them really look the same on the different technologies. Basic components are you're going to have a suction check valve on the bottom, discharge check valve on the top, and then your diaphragm is in the liquid end, and that is what's keeping your liquid from transferring back to the gear case of that pump. But when we take a look at what the back end of this pump looks like, so this is a hydraulic diaphragm pump, and you're going to have a reservoir in between the piston and the diaphragm. That piston is going to be moving in and out. It's going to be imparting force on the hydraulic liquid, and that's going to push the diaphragm out. And then you'll have a spring return, as well as the piston, when it strokes back, is going to create a suction to assist the diaphragm back. So we've got an animation here showing that operation. In the gear case of this pump, you've got a worm gear and then a cam that is pushing that piston in and out, turning it from rotary motion into linear motion. The yellow liquid that's moving around is hydraulic fluid. You can see the pistons compressing it and moving that diaphragm in and out. That bottom check valve will unseat on the stroke back, and then the discharge check valve, when it strokes out, is going to unseat, and you're going to push the liquid through the discharge. So mechanical diaphragm pump, like I said, the liquid end is going to look very similar. This one has 2 check valves in the picture, but in a mechanical diaphragm pump, you are going to have the piston is going to be mechanically linked to the diaphragm. So here we're showing a threaded diaphragm shaft off the back of the diaphragm, and you've got a worm gear again with a eccentric gear. That's what's pushing the piston out, and then you've got a spring return that will return the diaphragm. Closer look at that liquid end shows you how that threaded diaphragm, that the stud is molded into the diaphragm. Again, we've got a double check valve on this pump on that cutaway, but very similar, suction, discharge check valves, diaphragm, and your liquid head. Here's an animation. Again, we're turning the rotary motion into linear motion with a worm gear and then a cam. This one is pretty rough, but you can see that the green piston is mechanically fixed to the diaphragm, creating that motion back and forth, unseating the check valves. On the suction side, pull liquid in, and then when the diaphragm pushes, it's going to unseat the discharge again and move that liquid out. Okay, to depart to a different technology here, Brad touched on solenoid-driven pumps. So here's a cutaway of that design. And what this, in a basic sense, what this pump is doing is you've got 2 magnets, an inner and an outer magnet. And what happens is that outer magnet is going to energize, pull that inner magnet forward. It's mechanical, so that inner magnet is affixed to the piston and diaphragm. So when you energize that outer magnet, push the inner magnet in, and that is going to create the discharge stroke, and then you'll have a spring return that will bring it back for the suction stroke. We're showing you a manual stroke length adjustment knob on the back, so that's just going to limit how much the length of that stroke, and with each stroke how much displacement there is. A lot of these pumps will also come with a speed control, so you'll not only be able to control the length of the stroke, but also the speed of the stroke to adjust your flow rate. And then the last design we're going to cover is the stepper motor. So you'll see on the bottom there by the arrow, that is the stepper motor. The shaft is vertical up, and then you've got it's belt driven, and then that it's hard to see, but that's that's where you're going to create your linear motion. Taking a look at that technology. So stepper motor, if you take a look at that top picture, what it is you've got a rotor and then a stator, and the stator has individual windings. You'll notice that the rotor in this depiction has 4 points on it. The individual stator windings, you've got 6 of them. So what happens is you're going to engage those different windings, and because the points are offset, it will slowly rotate as the windings are engaged. So you're going to have typically a digital interface that's causing those to fire in sequence. On the bottom, you see, we start in the 12 o'clock position, then another set fires, you move to a 10 o'clock position, and then an 8 o'clock position. Then we've got an animation of what that looks like. In this depiction, there are 8 stator windings, and the rotor has 6 points on it. So you'll see it as those fire, as you ground each stage, it rotates. So now we're going to have a video that's going to talk a little bit more about the stepper motor, as well as some of the features that you'll find on some of these pumps. So today we're going to take a look at the Grundfos DDA. What we have here is a DDA 17.7 that is a 2 gallon per hour pump. And what we're going to talk about is just going to feature the stepper motor and what that means for pump operation, and then talk about some of the features of this pump that can be very helpful for applications. So the first thing that I'm going to do is I'm going to go ahead and turn the pump on. Right now I am requesting 0.7 gallons per minute, or excuse me, 7 gallons per hour. So I'm going to go in and make a change to that, request a higher flow rate. So I'm going to turn the pump up. Let's get it up to 1 gallon per hour. So now you heard that pump speed up as I turn the dial. The thing to look at in this acrylic head is that the diaphragm, no matter what speed the pump is operating at, with that stepper motor, it's always going to have the full stroke length. It's just how fast that stepper motor is firing. So, as you speed up, you'll hear the frequency. As you're speeding up, going faster, diaphragm moves out faster, but always the same stroke length. So now, what we're going to take a look at, I'll turn it down back to 1 gallon per hour. So we're set at 1 gallon per hour. What I'm going to do is highlight the auto flow adapt feature. So right now in the settings, I have the auto flow adapt turned off, and I'm going to simulate a cavitation event. So I'm just going to crimp this suction line. And if you look at the interface, I'm requesting 1 gallon per hour, and you can see down below, the flow sensor is telling me I'm currently at 0.5 gallons per hour, and it's dropping. In the head, you can see air bubbles, so it's not fully displacing. It's about half displacing my required flow right now. Pump is not adjusting, and I'm just getting less flow. If I crimp it all the way down, it will go into alarm mode. So if you've got an alarm cable on here, you can send it back to a control panel to let you know. Otherwise the screen lights up, let you know that there's an issue. So I'll let it go and prime again, get back to normal operation. And then we're going to go into the interface, and we are going to turn on that auto flow adapt. So I go into settings, scroll down, confirm that I want to turn that on. Immediately you hear the speed of the pump change, the frequency. So I'm going to get out of this screen, get back to the main screen. You'll see that I'm still requesting 1 gallon per hour. If I again simulate that cavitation event, as that suction line is not allowed to pull that full flow, the pump will speed up, and it's going to try and recover, run faster. I crimped it down too hard, so it goes straight into alarm. But if I let it run, the suction line fill, it slows back down. It's sensing currently we're asking for 1 gallon per hour. That's what it's hitting. If I just loosely crimp down, hear it speed up. If I'm still allowed to pull fluid, it's hitting that 1 gallon per hour. just running faster to accommodate. And if I clamp fully down, so it can't pull fluid, I'll go into alarm. So that's auto flow adapt. So other features that I want to show you on this DDA with the flow control feature, if I go into settings and I can turn on slow mode, and that can do a few things for you. It helps with off-gassing liquids like hydrogen peroxide, sodium hypochlorite, where when you're shut down it'll build air in the line. It also helps with viscous fluids. If you're trying to pull a viscous fluid in, what the slow mode does is create a longer, more gentle stroke length to encourage that liquid to come in versus just fast, quick strokes. The next thing would be the auto de-aeration feature. So when you're taking a look at liquids that are off-gassing or entrained air in liquids, a lot of times it'll go into alarm mode and it will shut the pump down. This feature will encourage those air bubbles to go out of the pump and de-aerate so you can get back to normal operation. Okay. So one thing about that I want to offer up is we do have that DDA demo unit. If you have any interest in playing with that unit at all, going through the different features, taking a closer look at it, you can reach out to me or an inside person or an account manager, and we can bring that to you so you can check it out. So we're going to move on to our next polling question. This is going to be a softball one for everybody. For a pump with a 10-to-1 ratio and a maximum flow of 10 gallons per hour, minimum accurate flow is 10 gallons per hour, 1 gallon per hour, 0.1 gallon per hour, or 0.01 gallon per hour. Okay, so we've got several different answers here. The majority did pick 1 gallon per hour, which is the correct answer. So that when sizing a pump, we want to take a look at what is our flow range and make sure we're sizing it such that we're going to get accurate performance in that range. We will talk about that a little bit more in a bit here, but I will go ahead and turn the presentation back over to Brad to talk about control methods.
All right, thanks, Tom. So what I'm going to roll through here is different ways to control the pump, both locally at the pump. So how to manipulate the pump, and Tom showed some of that in his video a second ago. How to control the pump locally, so turning the dials, pushing the buttons, those sorts of things, like what's capable there and how you do that. But then also common control features externally, right? So remotely from a PLC or a manned control panel, some of the different inputs and outputs and abilities, ways to control dosing pumps from an external point of view. All right, there we go. 3 main ways to control a dosing pump, right? First one, most common on a solenoid, like Tom had talked to, and myself, is changing the stroke length. So that is how far the diaphragm moves from its original origin position point all the way to 100% strength length. There's the ability to change how far that moves, right? So hypothetically, if you had an 8 gallon per hour pump and you wanted 4 gallons per hour out of that pump, one way to achieve that is to do 50% stroke length. So all you're doing is moving the diaphragm 50% of its total available length, achieving half of the full flow. The other thing to do is the frequency. So changing how often the diaphragm moves. This is what Grundfos does with our I'm sorry, this is the solenoid pumps. This is how far and how often the diaphragm moves. So on the stroke length, you can change how far it moves, and then you can change how often it moves. So between the two of those, say you had your same 8-gallon per hour pump, you needed 2 gallons per hour out of that pump. So you can change the pump to run 50% stroke length, which then gives you 4 gallons per hour. And then if you did 50% stroke frequency, then that only runs half of the time. So then that achieves the other 50% turn down. So you go from your 8-gallon to 2 gallon per hour. There is some, you can change that intermittently between applications. The one thing you run into, and this came up in one of the polling questions earlier, was anytime you change the stroke length, so you don't go 100% of the discharge length, you run into airlock situations, right? So you've got a pump, say you're pumping sodium hypo, in which was already high properties of gas, and you're not doing 100% stroke length. Sometimes you can run into situations where you're building air in the head, unable to get the air out of the head, and that's when you'll vapor lock the pump. Another way to run is VFD. So just like you do on centrifugal pumps, you can run dosing pumps on VFDs. All you're doing then is changing the frequency or the speed. So instead of running at 60 hertz, you can run at 30 hertz to get 50% speed, and you're just controlling how fast that diaphragm moves. Yeah, so that's kind of got a little ahead of myself there, but say you had an 8-gallon per hour pump and you wanted 2 gallons per hour, which would be 25% of that rated capacity. You could do 50% stroke length, so the diaphragm moves 50% of its full length abilities, and then 50% of the time. So half the time the pump is not running, and then you run between the two of those, you get 25%, or in an 8-gallon per hour pump, you could get your 2 gallons per hour. Typically that's done locally. This is common on solenoid pumps, in which there's 2 dials on the face of a solenoid pump, one of them being for the stroke length and the other one being for the stroke frequency. And you can adjust the 2 of those to dial in the flow rate that's needed. This is Grundfos kind of does a hybrid of the 2. So like Tom had shown in the video a little bit, Grundfos always does 100% stroke length. So whether it be 8 gallons per hour or 0.8 gallons per hour, Grundfos always uses, and this is utilizing the stepper motor, we always go 100% stroke length. We just change the speed in which the diaphragm moves. So an 8-gallon per hour pump, that diaphragm and the piston is going to run at 100% speed as fast as it can. At 50%, and say you needed 4 gallons per hour, the pump still runs at 100% discharge stroke length, but it runs half as fast, so half the speed of the 8 gallons per hour. And then if you dialed it down even further and you went to 2 gallons per hour on the 8-gallon per hour pump, now the pump is still running at 100% discharge stroke length, but it's now running at 75% slower speeds. So it's only running at 25% speed. The big advantage is there when you're pumping sodium hypochlorite, obviously, is every time that you do a discharge stroke length, you get all of the air and the water that was sucked into the head on the suction stroke pushed out of the head. So a lot of the times solenoid pumps in sodium hypo applications require, I think they're called degassing valves or air relief valves, that install directly on top of the head that allows for some of that entrapped air to be relieved. With the stepper motor technology, that certain component is not required, as it's built in with 100% discharge stroke length. And then on the VFD, so this is the same as as controlling a VFD on a centrifugal pump. All you're doing is changing the frequency in which the pump runs. Typically, they still run at 100% discharge stroke length, but your turn down is variable based on the motor and the drive. So on the solenoid pumps, I think you're typically 40 to 1 turn down, or 60 or 80 to 1 turn down. It may depend on manufacturer. Stepper motors are anywhere from 800 to 1 all the way up to 3,000 to 1 turn down. And so the VFD is kind of variable in that turn down ratio, depending on the size of the motor, the pump, and the drive itself. This is kind of an older technology. I'll state the VFD on a dosing pump is a little bit older technology. It's not seen as often, most commonly seen in applications where it requires an explosion-proof pump in which the VFD is run outside of the explosion-proof environment. So basically when you need a variable speed dosing pump, but you need it inside of an explosion-proof application, you'll see a pump similar to what you see here on the right, whether it be mechanical or a hydraulic dosing pump, but still needs some variable operation. Then you just put the VFD outside of that enclosed, that hazardous environment. So wiring considerations, this is all the inputs and outputs, right? And this is pretty constant and consistent across all dosing pump manufacturers. Most common 4 to 20 input as your analog input. So you would have remote control of the flow using a 4 to 20 input. Then you would also have a multitude of different options on your input over here on the left. You can have pulse. So anytime it's common in like floral. So where they're manufacturing plants inside of a greenhouse, you could have like a little plant, and every time that its vase or container goes underneath an optic signal, the optic signal sends a pulse to the pump, and the pump will dose whatever that feeding chemical is and into the base. So that's a pulse base. Analog, a lot of times you'll see these are flow pace, so you'll have a process line, and the flow of chemical into the line needs to be linear with the amount of water flow in the process. So the more flow that goes through the process line sends a signal using a flow meter back to the pump, and then the pump speeds up as well. And then when the process line slows down, then the signal to the dosing pump slows down as well. And that would be like a linear relationship. Outputs, so typically your digital outputs are alarm relays. So if you have a remote controlled environment in which there's a control panel that's manned, typically there's outputs from the pump back to the control panel that signify any sort of alarms, any sort of faults, anything going on with the pump. At the same time, it can also send a constant signal that says the pump is dosing. So you don't have to walk up to the pump manually or locally to the pump and see that it's actually dosing. There's outputs available. So you can sit in the remote controlled environment and still know that the pumps are running. And then there's also analog outputs. So your analog outputs could tell you the flow the pump is putting out, the pressure the pump is putting out, or if you're running it on a 4 to 20 input, if your system is signaling it 10 milliamps, then there's verification back out from the pump that says the pump is receiving the 10 milliamps. So there's a multitude of different wiring and control considerations for these dosing pumps. So turn down, I'm not an expert on turn down. It's a very technical discussion, I guess, but basically what turn down does is it provides an area of performability in which the pump can maintain a certain repeatable accuracy in, right? So like the last poll question said, in a 10 to 1 turn down, you're going to get anywhere from 1 to 10 gallons at whatever given accuracy that is. In the stepper motor pumps, on the smaller ones that you see here, we have at 2 gallons per hour, we have a 3,000 to 1 turn down, so that's 0.00067 gallons per hour, all the way up to 2 gallons per hour, which is about a half a teaspoon an hour, and that's plus or minus 1% of repeatable accuracy across that range. So what turn down's doing is turn down is giving you an area of capable performance from the pump, but still being able to maintain an accurate pump. After the 3,000 to 1, the stepper motor goes to 1,000 to 1. So if you had an 8 gallon per hour pump running at 1,000 to 1 turn down, you could go anywhere from 8 gallons per hour on the high side to 0.008 gallons per hour on the low side and still maintain that 1% repeatable accuracy within that entire range of 0.008 to 8 gallons per hour. That's kind of the easiest way to explain it. It gets very technical, and honestly, I'm not so versed on that, and that's exactly what this explains here. So this says the flow range dosing pumps 0.0067 gallons per hour on a small smart digital pump like Grundfos has at that 3,001 turn down, up to 9,000 gallons per hour, which is one heck of a dosing pump. But anything within that range, there is products out there for anything within that range. So this is kind of this is how it can be controlled manually. So here you'll see like this dial on the right. This is percent speed. So this would be like 0% speed if you needed. Say this was a 4 gallon per hour pump and you wanted 4 gallons per hour, you would set it to 100%. 50% is over here. The reason for the non-linear scale is because you want more resolution and accuracy at the lower flow rates. So a lot of the time, some of the issues is users have a 4 gallon per hour pump. They say, I want 2 gallons per hour out of this pump, and they stick this little knob straight up, right? Well, it's straight up, you're at 3.5 gallons per hour, and you're obviously not going to, sorry, 3.5% speed, and you're obviously not going to capture 2 gallons per hour. So this is how you would control it manually. These are kind of the inputs and the outputs for your alarms out, your 4 to 20 ends, your pulse signal ends, those sorts of things. This is kind of the interface of the pump. And with that, I will turn it back over to Tom unless there's any questions.
Okay. So we're going to talk a little bit about pump selection, but that's a good point. Brad, if you guys have any questions, please put them in the questions chat box. We will answer those afterward. So considerations for selecting a pump, you know, it's a lot of the same stuff that we get into with centrifugal pumps or other PD pump designs. The one thing I would caution you with a dosing pump is that a lot of time we are handling hazardous chemicals that could potentially hurt somebody. So it's important to get all this information so that you select something that is going to work and not harm anybody. Right off the bat, you're going to need, what do you want that pump to do? What kind of performance are you looking for? What flow and also what pressure does it need to overcome? Usually when we're looking at dosing pumps, I prefer to size that pump for 90% of the max capacity flow rate you're looking for. It's kind of like when you're selecting a centrifugal pump, if you're running that fixed speed, you don't always want to pick the max diameter impeller, just in case you've got future additional demands or you underestimate, what kind of flow you need. Liquid properties, just thinking about all the different things we talked about, off-gassing liquids, hazardous areas. We'll run through a couple of those different liquid properties, but anything that would make the application difficult. Chemical compatibility is very important. You don't want to select a pump that has incorrect liquid end materials or, elastomers, which, is going to cause that pump to fail quickly. Then turn down capability and accuracy. Similar to the first point, you want to give yourself some flexibility on the bottom end. Brad talked about accuracy ranges of pumps. You want to make sure that that you can fit that pump in and have your minimum point and give yourself some extra flexibility at the bottom if possible. And then when selecting the pump, the control method, you got to make sure you select that pump the way that you want to adjust it. So a typical dosing performance chart, it's pretty simple. Across the x-axis, you got the flow rate, and then across the y, the pressure. So taking a look at this pump, it will be capable of anything within that squared off range. So this pump is going to have a top end of about 0.625 gallons per hour and max pressure of about 260 psi. Got an arrow on here pointing out that cross section. So if I was looking at this application for 0.2 gallons per hour, it needs to be able to accommodate 120 psi. This would be an option for us. So liquid properties, a lot of things to think about. Is it a corrosive liquid? Is it going to be hazardous to people? We got to make sure we select compatible materials that aren't going to react with your pumpage. Abrasives, this is one we don't run into a whole lot, but if you were, I personally don't, but if you're handling something like titanium dioxide, bentonite clay slurry, something with diatomaceous earth, you may want to consider potentially going to a larger pump and slowing it down to increase the life of that pump, or potentially maybe even looking at a different technology. Because the area with the checks, the suction and discharge valve, we can tear those up pretty quick in the high pressure areas. Temperature, just like any pump, it's kind of self-explanatory. Whatever that pump's made out of needs to be able to handle the temperature that you're seeing. Your viscosity. So this one is kind of twofold. And what we're concerned about there is with viscosity, the first thing is being able to prime the pump. If you've got greater suction losses on the suction side, we talked about slow mode on that stepper motor, on that option on that DDA, to help encourage that liquid to pull it into the pump. We can't, we're not going to be able to pump that liquid if we can't get it into the pump. So, and then the second thing with viscosity is with the check valves. If you get over a couple hundred centipoise, you may have problems with those valves seating properly. You may want to take a look at spring-loaded checks. And then the next thing is solids. Pretty straightforward. If you can't get into the pump, you can't pump it. You might want to consider if you've got liquid you're pumping that has solids that settle out, and you do need to handle those to agitate your drum or your tank to keep them in suspension. In train gas, we talked about air in that liquid end is gonna compress, so that's gonna affect your accuracy. So you may need some specific features to handle that. Same with off gassing. If liquid sits like hydrogen peroxide, sodium hypo, could easily vapor lock a pump. So there's different things like off gassing valves, as well as different features in the pump that can help you handle that. Concentration of that liquid, that goes back into chemical compatibility. We'll talk more about that. Vapor pressure of the liquid. If you're pulling a lift, you do not want to pull that liquid out of phase. So it's very important taking a look at that if you're on the margin of what you pull. And then the last thing is any other special features. Do you have, is this pump in an explosion-proof environment? Do we need a class 1 Div 1 motor? Do we need, do you have special, does that liquid have special flow properties? Is the pump in a corrosive environment where potentially the air could attack, the internals of the pump if it's not completely enclosed, or just anything that could potentially cause that pump to fail prematurely or make it difficult to either prime or process your the liquid. So chemical compatibility, just going to run through this pretty quick. 3 things you want to talk about with this. You don't just want to look at the liquid and find out if it works with your different materials. You need to also consider concentration and temperature. As the concentration goes up, you look at acetic acid there, especially in the gasket material area. In some cases, at the lower concentration, it's okay. And as we increase the concentration, we're probably going to run into problems there. And then also coupling that with temperature. As the temperature increases, some chemicals get more reactive. So you want to consider all 3 when you're selecting your materials for your pump. You have this disclaimer on the bottom that says most manufacturers don't recommend any material for any application. Field experience can be the best guide. Really successful experience is the best course because you've done it before, you know it works. But we can give you recommendations. We look at these different compatibility charts. I prefer, when I'm selecting any pump, dosing pump or other, I prefer to start with that manufacturer of the pump I'm looking at. Typically has a chart. I start there. If I know it's something that's going to be difficult to handle, I may look at a secondary chart. One that I do use quite often is Cole-Parmer. So if you go out to coleparmer.com, they've got a pretty nice tool. You look under product support, and this is what you get. You get a selection of your chemical and or your material. So you can just drop your chemical in there and take a look at all kinds of different materials. You can also do it with just selecting the material, or if you want to get right to the point, your chemical and material, it will give you a compatibility rating. Obviously, we want an excellent rating. In some cases, we will go to a good rating if it's a very difficult chemical, and depending on what options are available with that pump. So we come to our last polling question. And the question is, what is your comfort level with dosing pump technologies? I've never used a dosing pump. I have some experience with operating dosing pumps. I'm familiar with sizing and selection for dosing pumps. They're all the same to me. So it looks like we've got a range. I am glad to see that they're not all the same to everybody, especially since we just went through all the features, control where they're used. So that is good. Okay, so I'm going to turn it over to Brad for installation and piping practice.
Yeah, I think this should finish out the presentation. So thanks everyone for hanging in. I'm going to run through kind of some installation, good and bad, where we see some problems, some easy things to overcome. I know installation is a big part of some of the issues that people have. Material compatibility and then how to properly install these things is often an issue, and I don't think I have control. Oh, there we go. So starting here, this is kind of the typical system components. So this is all of the components that are typically needed, right? So over here, you see number 1 and number 2, number 1 being the chemical tank. This is where the chemical would be housed. 2 being, this is a mixer. So typically, you want to agitate the chemical a little bit just so it stays fluid, it doesn't coagulate, and stays good, I guess. 3 is a calibration column. This is important to make sure that the pump is properly calibrated. This goes all the way back to one of the first things I said about correctly using a pump for high accuracy, right? Because chemical is such a high cost, probably the most expensive component of a water treatment system. And properly calibrating the pump. All pumps, at least I know from Grundfos, I would bet from all manufacturers, are calibrated at the factory where they're built, but they're calibrated with water, right? So water obviously has different properties than a caustic or sulfuric, and it's important that once the pump gets to the field that it's calibrated for the liquid that it's going to pump in the application that it's going to be in. And that just ensures that that the pump operates as it should be. Item 4, being a filter. Typically, you'll just see this as like a Y strainer. Item 5 is the pump itself. Item 6 being a pressure relief valve. So if the pressure in the line gets too high, that valve will open and typically send the chemical back to the tote to relieve, so you don't overpressure, right? A lot of these are standard PVC or CPVC tubing applications in which there's a given rating, pressure rating, and if the system overcomes that pressure rating, something's going to pop, and then you're spewing chemical all over the floor. 7 being a back pressure valve, so generating pressure back onto the system. All dosing pumps, regardless of the type or style, require back pressure, typically 30 to 45 pounds, and that's to ensure that the check balls in the dosing head work properly. The better the back pressure on the line, the better the check balls work, and the more accurate the dosing pump's going to be. Number 8 would be a pulsation dampener. Number 9, a flow meter. And then 10 would be your injection quill, and that injection quill would then dose the chemical into the process line that you see with this tube cutaway. So that's kind of your typical system components. What we're starting to see a lot is manufacturers and distributors like Crane offering skidded systems, right? So what a skidded system would be everything 1 through 8, you know, everything in this circle on a common frame. Put it on a plastic frame or a steel base, and the manufacturer or provider of that system hydrotest everything. It's a single source contact for all the components. You're not buying a pump from the pump manufacturer and the tank from a tank guy and kind of piecemealing this thing together. When you offer and provide or supply skidded systems, there's some sort of assurance that all of the components that are provided are properly engineered and supplied for that specific application. So that's also something to consider in all of this. It takes a little bit of the liability off the user, and more onto the supplier and the manufacturer when you go with a skidded system. So this is a very, very basic setup, right? So this would signify your pump. This is your chemical tote down here, and this would be a suction lift application, which most of these pumps are. So there was a question earlier about the suction length. Suction length is variable based on the installation. So the better the system, the better the installation, the longer your suction length can be. And as straight as your suction length is, or your suction tubing or piping is, the longer that suction length could be. Most of the time, suction side questions are around suction lift. So how far up can a dosing pump pull the chemical? And that's variable per manufacturer. Grundfos is 18 feet with wetted check balls, and I think 3 meters, which would be 9 feet without. And I'm not too familiar with other manufacturers, but I know manufacturer suction lengths depend on themselves. So this is a very basic manual. You've got a pump here, you're going to operate it locally, and it's going to dose chemical from this green tank into the process line. That's about as basic as it gets. So here's kind of a typical feedback system, right? So this is where you're controlling the pump externally, monitoring it externally, and it's being operated with a controller. So some sort of monitoring control device, like I know Hawk is common in the wastewater industry for residual readers. So it measures a certain parts per million or certain chemical property in the line, determines that additional chemical is needed, and it sends a signal to the pump, and the pump operates that way. That would be an automated system in which this controller is utilizing the sensor. The sensor sends a signal to the controller. The controller generates a 4 to 20 input signal to the pump, and then the pump would operate based on that feedback. Same sort of install here, though. This is One thing I didn't point out in the last slides is every vertical installation and where the pump is pulling from a tank requires a foot valve. This foot valve acts as a check valve in the bottom of the tank. Once the pump is primed, then a properly working foot valve will maintain prime in the suction line, both the line in the tank and the line into the pump. Without a check valve in the bottom of the tank, all you're going to do is after you achieve prime, then all of the liquid that's primed in the line is just going to fall back into the tank, and you're just going to find yourself repriming and repriming and repriming. So anytime there's suction side disturbances, it's either one of two things, and that's one of them, right? So you have a faulty check valve or a check valve that's gooped up with crystallized chemical or something along those lines. So that's one thing I always recommend checking, flushing out is the foot valve with suction side problems. This is a basic diagram of the automated control system as well. So you've got a sensor on the intake side in which it's measuring a certain parts per million. You've got one on the discharge side, and they're sending signals via a controller back to the pump to increase flow or decrease flow to maintain a given set point or residual in the process line. Yeah, so here's another standard installation tank. Foot valve, like I said, is critical to maintain prime in the line. You've got your dosing pump, your injection quill, which this has a check valve in there as well, and it's what injects chemical into the line and prevents siphoning back into the pump system. So here's the other problem with suction side. So even in situations where there is a foot valve, that's step number one, is to make sure your foot valve is clean, it's clear, and it's not goopy. The second is to look at the suction line. So as you can see in my previous slides, ideally you want a vertical line from the tank to the injection point. Here's where we run into big time air problems. So even when you do prime a line, you run into situations where air gets in the line, and especially in something this squirrely where you get air, or you get a lot of the times I see where the suction tubing is coiled up. So you've got a straight line into your tank, you've got the pump sitting up here, but then you have suction side tubing that's just coiled, right? Well, it's impossible to keep that prime because the air always floats to the top, and then you create all sorts of suction side air problems. These are bad. So anytime you can straighten out the relationship between the injection valve, the pump, and the foot valve and create something very linear like this is an ideal situation. These are not. So you want to keep as much vertical rise in the suction side as you can. The discharge side's not as important because the discharge side, in a properly designed system, there's adequate back pressure onto the discharge line, as I mentioned earlier, typically 30 to 45 pounds. But that helps prevent some of the errors, is that properly pressurized discharge line. It's the suction line that gives us the most problems. So this goes back into the question from earlier. Large suction heights. So the only reason that we recommend a shorter, in a situation like this, we would always recommend the pump be closer to the tank as possible, because the suction line is what always gives the bigger problems. The discharge line, like I mentioned a second ago, should always be pressurized. And so the longer you can keep that pressurized run on the discharge side, it keeps the suction side shorter, which will always eliminate or reduce the number of suction side disturbances. I don't know that this value is correct. I've seen applications in which suction side heights are much longer than 2 meters, but as close to the discharge, or as close as the chemical tote as you can get the pump, the better. And then obviously this is no good either, right? So all this area up here is going to do is build air. So any sort of situation like this where you had to have a pump on the bottom with the tank, I would always Flooded suction, have a flooded suction application where your chemical comes off the side of the tank, fills the dosing pump with positive pressure. Make sure that the top of the tank is vented so you have atmospheric pressure down that pushes chemical into the tank or into the pump, and do it that way. This is no good. This is always going to give you air problems. Any sort of bends like this on the suction side are always our biggest issues. Yeah, so we also see this a lot where there's a chemical that needs to be agitated. So it's either a chemical that's not run very often or used very often, or some sort of polymer that's viscous that you want to keep agitated so it doesn't gum up. In those situations where you have a mixer or an agitator in the line, please be sure that you always use a rigid suction line. Obviously, as this agitator spins and creates, all this is going to do is pull this suction line and probably wrap it around this tank or this mixer, and that's never going to be a good situation. So just be sure that you have a anytime you have an agitator, you have a rigid suction line. It could even be just like a PVC shield over a tubing, which is fine. And then keep your foot valve 3 to 6 inches off the bottom. This helps keep debris and goopy stuff from getting into the bottom of the foot valve. And I think that's all I had. Turn it back over to Tom to close us out. Thank you.
Okay, just to recap what our objectives are. If we didn't cover something, I would invite you to throw a question in the chat box. But I think we hit on most of these points where you want to describe where and why dosing pumps are used, explain the mechanics of a common dosing pump design, demonstrate basic steps to select the pump, describe typical control methods, and Brad closed it out with identifying good installation and piping practices. So now we will take a look at what kind of questions we do have and see if we can answer those.
All right, thank you, Tom and Brad. We do have a few questions here that came in, so I'll tee a few of these up for you guys. A couple of them were addressed. There were some questions about the maximum suction length and ideas for proper installation. So I think Brad did a good job covering those already. But here's one. Customer is asking, between diaphragm pumps and stepper motor pumps, what percent are stepper motor pumps, or I guess what percent are customers buying that are stepper motor pumps? They're wondering if they're still using a diaphragm pump instead of a stepper motor. Are they using outdated technology?
Well, I would say that we look at all technologies. You know, there's some cases if you don't need accuracy, we might even use a gear pump. But we take a look at them all. Brad touched on, you know, where you might use a hydraulic pump, high pressure, explosion-proof environment. We do, you know, for a lot of applications, we do look at the stepper motor design just because of a lot of the features that are there. But there may be some cases where you don't need those features, and there's other products that do have the features you need and the performance you need. So I wouldn't say it's behind the times. I would just, you know, it's a good idea to be knowledgeable on what's out there, and some of the different features may make your life easier and with different applications. So I would still apply all of these technologies.
Okay. Thanks, Tom. Brad, anything to add, or does that cover it, you think?
Yeah, I mean, so where so the solenoid pump and the hydraulic and the mechanical pumps are a much older technology, right? So they've been around for decades and decades. So the stepper motor being a newer technology within the last, I don't know, 8 or 10 years, obviously you know, anytime a newer technology is introduced, there's some skepticism, but we've seen a huge increase in awareness to the stepper motor pump. We've seen a huge increase in supply of stepper motor pumps to the field. I don't really know. I mean, I'm biased. I work for Grundfos, and we only provide stepper motor pumps, right? So I wouldn't be I wouldn't know the ratio of what's out there. I would assume that there's more solenoid and there's more other pumps out there. Non-stepper motor at this time, just based on the sheer volume that, or the sheer fact that the stepper motor's only been around for 8 or 10 years, and it takes some time. You know, moving to a stepper motor and some of the features is kind of a cultural change, right? It's a completely different animal than a traditional solenoid, and so there's some skepticism. It takes a little bit of time, but I think the shift is moving to that stepper motor technology. But I wouldn't have a clue in terms of ratio of stepper motor to other technologies.
Okay, got it. Thank you guys. So definitely not a one size fits all approach. Sounds like stepper motors are gaining popularity, but certainly good to look at the right pump for the application, considering all the process details. We got a few more here, guys. Could one of you speak to typical diaphragm materials, some of the more common materials that are used for diaphragms?
Yeah, I can. So on a solenoid pump, most solenoid pumps are the diaphragms are two pieces. It's a rubber, I don't know material rubber, but then there's a PTFE laminated diaphragm to that. So the exterior, the portion that should be touching the chemical is PTFE, Teflon, but it's laminated to a rubber. We call it a rubber backed diaphragm. Over time, that lamination, just like any lamination, tends to separate, in which you run into performance issues once your diaphragm starts to split. I think every manufacturer out there is providing a diaphragm that is Teflon, just because it's the most universally accepted material for chemicals. Grundfos only does full Teflon materials, diaphragms. We don't have a rubber backed, just because we saw so many issues with delamination between the PTFE and the rubber backed diaphragm. Ours are only full PTFE, but that's most every manufacturer is going to be Teflon, just because of the compatibility component.
Awesome, thanks, Brett. Another question, but a good, I guess, add-on to the last one. What has more of an effect on diaphragm life, stroke length or frequency?
I really have no idea. I would guess frequency. I don't know. I can ask. I don't know. I would guess frequency, just because the diaphragm would be used more. The more the diaphragm's used, the more wear and tear it's going to get, I would bet. I can clarify that with my engineering team in Germany and get back with Tom and Dustin to follow up. But my guess would be frequency, but that's just purely a guess. Just because it's used.
Yeah. Okay. All right. So we will we'll follow up with the customer who asked that question, make sure we get the correct answer on that, and we'll get back to them. Quick one here. What do we need to do to get continuing education credits? So not related to dosing pumps, but there will be, as soon as we conclude the training here, the Q&A session, a survey will pop up. If you complete the survey, that will allow you to be eligible for the CE or DNR credits. Morgan will also send an email within 24 hours. So if you don't have time to do the survey now, you can complete the survey when you get the email from Morgan. Another question here. What thread sealant do you recommend to seal MPT plumbing with looks like 12.5% bleach? Any comments on the thread sealant?
Off the top of my head, I would suggest Teflon, but that's something that we can get back on as well. I'm thinking Teflon would be the #1 answer I'd go with.
Okay, thanks, Tom. Next question here, guys. In the presentation, the flow rate was displayed on the Grundfos dosing pump. Was this flow rate measured using an external sensor, or does the pump calculate the flow?
It's a calculated flow. based on some giant algorithm that I don't understand. But it is a calculated flow.
Okay, and then what would be the expected accuracy for that calculated flow, Brad?
I mean, it depends on the system, right? So if we are confident in plus or minus 1% if the pump is installed and operating properly. So if the suction and the discharge lines are installed properly, if the pump has been calibrated in the field with the chemical that it's running, if there's proper amount of back pressure, given all factors are correct, we can ensure plus or minus 1%. But it's, the biggest issue with accuracy in the field is pumps are not calibrated in the field. Pumps are calibrated, I think I mentioned, in the factory with water, and water has drastically different properties than all the other chemicals that these are used on. So given all things are equal and correct, we would say 1%.
All right, thanks, Brad. When it comes to dosing pumps, are there different PMs or things you can do to extend the life of the dosing pump? And I guess typically are they run to failure, or are there things you can do to kind of predict, take more of a predictive approach and predict the life you're going to get out of the pump?
Yeah, so, and I can talk to this on all of our DDAs, which is the one that Tom showed in the video demonstration. We have an integrated service log. Every 8,000 hours, the pump will trigger a yellow screen or an orange screen that is a kind of a heads up, a warning screen that says, hey, preventative maintenance should be performed on this pump at 8,000 operating hours. Service should be performed on this pump. It's typically replacing the check valves and it's replacing the diaphragm. When this happens at 8,000 hours and the pump goes into orange, you go into the service screen, which is done how Tom showed you in the video. It will tell you the 8-digit part number that you need to order to complete the service on there. It can be reset at that point. My rule of thumb is if it's not broken, don't fix it, right? So if it triggers at 8,000 hours and the pump is running just fine, I wouldn't start pulling things apart. I would then also recommend having a spare service kit in a situation in which the pump does go bad or a valve or diaphragm does need to be replaced. If that happens, if there's a diaphragm tear, or if say you get some goop in the head and the check valves aren't seating properly, so they don't sit back down, the pump will notice a pressure loss and it will signify that the check valves are bad. So in that situation, even if that's before 8,000 hours, the pump will tell you that there's a check valve failure and that you need to replace the check valves, and then it gives you that 8-digit part number to call Crane and order. But then at 10,000 hours, so say you ignore it at 8,000 hours, at 10,000 hours, it'll go into another alarm in which it tells you to do it again. You can ignore it. My rule of thumb is if you're not having any performance issues, ignore it. As easy as maintenance is on these pumps, you can swap out a repair kit in less than an hour. So my rule of thumb is if it's not broken, don't fix it, but the pump will tell you if it's broken before 8,000 hours, or it'll tell you to do the preventative maintenance at 8,000.
Perfect, thanks, Brett. If an add-on to that one, if applied properly and correct materials, installation's good, and PMs are done as recommended, what's the typical life expectancy for a dosing pump?
Yeah, I get asked this a lot. I don't think we publish anything because I think then we assume liability there. I don't know. Years and years. Yeah, 6 or 8 years, maybe 5, 6 years. I've seen them last. I mean, I've seen them last forever. But we don't. I don't think. I'll double check, but I'm pretty sure that we don't publish average life expectancy, just because then that gets us in trouble with warranty issues when if a pump doesn't make it 6 years or whatever, then people look at us. So I'll double check, but I don't think we publish that, and I don't know that I have a good number there.
Okay.
Long time. I'll go with that.
Sounds good. All right, guys. Well, that does it for the Q&A. So again, thank you everybody for attending. We hope you learned some things along the way here, and hope you enjoy the rest of your summer and have a chance to join us for our next session in September. So again, don't forget about the survey that should pop up here shortly, and enjoy the rest of your week. Thanks, everybody.